Working on a 2004 Chevy Aveo, the 1.6 liter engine. This is the one that had the misfires on all the cylinders after the guy did the timing belt incorrectly. So we're just going to do some real quick checks. I know it is running real rich, but so cylinder one there, I got my compression hose hooked up to my pressure transducer for the first test on channel A. What I'm going to do is I'm going to go ahead and start it. If you go ahead and start it, let it idle. I'm going to change our time scale here. And let me change a little bit more. And we're going to look at that and see our back pressure. Alrighty, so if you look here at the scope, from this point, that point to that point, 720 degrees of crankshaft revolution. Between there's 4 strokes: power, exhaust, intake, compression. Right there's the exhaust stroke. I'm at idle. I don't even have 1 psi. Right, I got 975 milli psi, so 0.975 psi. Now what we're going to do is rev it to 3,000 RPMs because we want to have no more than 2 psi at 3,000 RPMs to ensure the cat's not plugged. Only reason we're doing this is because it had some multiple misfires. We want to make sure the cat is not plugged up. Already got it running again at idle. Go ahead and rev it to 3,000 and hold it. Stop. So I'm zoomed back in. We ran it at 3,000 RPMs. If you look, I got about 2.9 psi, which is approaching the threshold, but we're not quite there. A little concerning, but we're not quite there. Now all these other traces of line, that's just from that spark plug being off. I got to go into a test light to ground. You don't ever want to leave a spark plug wire not going to ground or going to a plug because it is very hard on the ignition coil. So what we're going to do now, we're within the specs, but barely. We're going to do a put a second channel up, which we got right here. We're going to go to the ignition coil with a 21 attenuator, because anytime you have a magnetic field collapsing on a coil pack, it can go over 100 volts, and the scope's only rated to 100 volts. Not that it will, but it could. Now we're going to check the timing on it, make sure the timing's not off. So now I'm going to check the timing on this vehicle to make sure it's good. It's firing at TDC or top dead center, because if you remember from the first video, I talked about they did a timing belt and it was off at 232. In which cylinder 3 piston hit the valves because they put the timing belt on wrong. Well, it's all back together, obviously, whoever did it. But it still runs like crap at idle. Misfiring on all the cylinders, running real rich, which could be some other issues too, but we still want to check the timing. So channel A, pressure transducer hooked up. Channel B, I got to my ignition coil. And I also have the wire that's off that spark plug number 1. I have it to a test light going to ground. Like I said, you don't want to leave an ignition coil or spark plug lead going open. You want to have it to go to ground or go to the plug. That way you're not wasting all that energy, because it will actually, not that you're wasting energy, it'll be very hard on the ignition coil. So 2 channels hooked up. Channel A, channel B, 21 attenuator on B. Why? The scope only handles 100 volts. Now I can handle up to 2,000 with my attenuator, because anytime a magnetic field collapses, whether it's an ignition coil, fuel injector, it can spike to over 100 volts. Wiring diagram: 3 wires, power. Computer controls the ground through a transistor, MOSFET transistor. Computer controls the ground through a MOSFET transistor. We're on cylinders 1 and 4 because we're on 1. Computer controls that transistor through ground there, and same thing for 2 and 3. 1 and 4, 2 and 3. But we're on the white wire there. So now what we're going to do is we're going to plate a scope, do a clear flood crank. We're going to smash the gas all the way to the floor, crank it over so it doesn't start. It disables the injectors, and look at our waveform. Go ahead, smash it to the floor and crank it until I say stop. Stop. So we're going to stop our waveform. We're going to back up, and what we're going to look at here is from one point to the next point, or one hump to one hump, this one to this one, is 720 degrees of crankshaft revolution. What that means is the crank turned over twice, right? 360 times 2. So now what I'm going to do is I'm going to zoom in and I'm going to check that, and we're going to go from there. So we're going to just watch that there. Have somebody else hold the camera for me. So like I said, from there to there, 720 degrees of crankshaft revolution. Sorry about the reflection, guys, but what we're going to do now is we're going to zoom in. Okay, so there's 720. What is this channel? Well, this channel here is A. This channel down here is B. Well, when the magnetic field collapses, this should be at the center, right? Because it always should spark at TDC, top dead center. So now, if you can see the whole screen now, there you go. This line, when it sparks, should be in the center of these humps, but it's not. It's off. It tells me it's too advanced. Like, it tells me that it's a tooth or two off still. Why? Because, like I said, when the magnetic field collapses, that's when your spark will occur off your secondary ignition. You got primary windings and you got secondary windings. When it collapses, this should be at TDC on the center of that hump with that pressure transducer. We can determine how far it's off by if we put some cursors in here. So if I measure the total from center, I mean, it's not very far off much. From there, it's a lot easier on a computer. That's good. It's there to there, from there to there. I got 518.2 milliseconds. So 518.2 milliseconds. So we're going to go back. We're going to do our calculator, which I always have a hard time finding this. There it is. So what did I say? 518.2. 518.2 from the center to the center. So I'm taking my calculator, clear this out, and we're going to do some math here. So 720 degrees divided by, what did I say, 518.2 milliseconds. That's 1.38. We'll call it 1.39 milliseconds per degree. So 1.39 milliseconds per degree. So if you take 1.39 times 720, you would get that number. So 1.39, go back to my scope here. So we took 720 divided by that. So if I get 1.39, that means for every degree, it's 1.39. So then what I'm going to do is I'm going to take my cursor and see how far it's off. So I'm going to zoom way in here just to measure, right? So that cursor there, we're off a little bit there, but pretty good. And then I'm going to go center to that. Actually, let me redo this just to make it a little bit easier on the eyes. Let's go like that. So there's our spark line. And there's the center, roughly. Well, the difference from the first to the second is 4.3 milliseconds. So if you go back to your calculator, times 1.39 times what I say, 4.3. I think that's what I said. 4.3. So we're off 5.9. We're off 6 degrees. So this bell tells me, or something's off in there, off 6 degrees for our timing, right? Now you could figure out there's 360 degrees in a circle. You could count how many teeth are on the cam pulley, the crank pulley, and all that stuff, and do some simple math that way and figure it out. But let's just check this again. Let's make sure I did my math right. Center. I have a software program on the computer. It's a little easier to use with a mouse, but my computer's dead right now, so we're going to do this. 514.7. 720 divided by 514.7. That means for every degree, yeah, 1.39, right? 1.39. So if you were to take 1.39 times, that's 1.39 degrees per millisecond times 514.7. Right, we're a little bit off because we rounded, right? But it would be 720 for revolution or degrees, 360 times 2. So our math is correct. But what that tells us is we're, like I said, 6 degrees off. Because this right here, if you look at this picture, this center line should be right on the center of that. It should be firing at TDC. Right now it's firing too advanced. If it's on the other side, it'd be firing on the retard side. So now it's firing too advanced. So that needs to be checked as well.